So like many of you, I've known Rebecca a long time. We were at AT&T together, and it's great to see so many old friends here today. Also, I started at Princeton, left AT&T in 2005, and about 3 months after I left AT&T, Rebecca started stalking me to get involved in DIMACS. So she didn't give me, sometimes you think give someone a semester to get settled, but then of course, by then they're too busy with new things. So Rebecca was smart. And she had a really great insight in 2005 that people were starting to think about reinventing the internet and making fundamental change to the internet architecture. And she thought, well, algorithmic foundation should be a part of it the second time around. And so we worked together on a program that she suggested, a special focus on algorithmic foundations of the internet, and ran a bunch of workshops. And now actually these kind of workshops are happening at DIMACS on their own without, well, at least maybe you're doing something, I'm certainly not. But I think that there's a community now in that space, and routinely many sessions at networking conferences on algorithmic foundations and various aspects of networking. The exact topic has shifted from year to year, or 5-year period to 5-year period, but now it's really a fundamental part of networking, and I think for the better. Networking is a field that sometimes lacks rigor and reinvents ideas, and it's been great to have a much greater number of networking people who are algorithmically informed, and also a lot more collaboration of networking researchers with people in the algorithms community. So what I'm going to talk about today is some recent work in that space of my own, but as part of a broader initiative within the networking community to take advantage of advances in the programmability of network devices. And they create a really nice opportunity to bring together ideas in streaming algorithms, particularly sketches, in new ways, where there's a nice new computational model. It's a little different than what some of the traditional sketch literature assumes, but close enough that a lot of ideas from theoretical computer science can be brought to bear very naturally in a very practical way. And so I'm going to talk about 3 projects of my own, but they're really exemplars of a body of work that quite a few people in the networking field are doing now. And a number of us think of it as the idea of a so-called self-driving network. So networks don't run themselves. Sure, routers, switches, react to failures and compute new paths. Congestion control adapts how the hosts are sending traffic. But to run well, you need to be able to identify congestion and reconfigure the network to route around it. You need to be able to determine what traffic is causing the buffers in your network to overflow, or to be able to identify cyber attacks. And so there's often a control loop, measuring the traffic and the performance, and analyzing that data, and then changing the configuration of the network accordingly to block an attack or reroute traffic to alleviate congestion. Now, when I worked at AT&T, I thought of these 3 tasks as separate from one another, and I thought of them as happening outside the network. The network would help in providing some of the data, but most of the analysis and control decisions had to take place above the network on a long time scale, in part because the network devices were just closed, even to people who owned them. Nowadays, that's not the case. We now have programmability in network devices, and it's possible to think about this control loop in an integrated way with a single set of abstractions around measuring, analyzing, and controlling the traffic at a small time scale directly as the packets are flowing through the network. And so I'm going to talk about 3 examples of that. One is microbursts, small timescale variability in traffic causing queues to overflow, causing packets to be delayed or dropped in the network. It'd be nice to figure out which traffic is causing that and block or slow down those flows so that the other traffic gets a fair share of the bandwidth. There might also be, on a longer timescale, heavy flows that are contributing a significant fraction of the bandwidth on a link, and you might want to block or slow those down because they're hogging resources. There might be a cyber attack. And finally, you might want to direct traffic over the current best paths in terms of performance, not just in terms of, say, hop count. So for all of these, I need to be able to find a needle in a haystack, which are the small set of flows causing microbursts, the small set of flows contributing a lot of bandwidth, and also maybe the small set of links that are contributing to congestion inside the network. And so there's a nice opportunity to try to have compact data structures to help do that, and then take the results of that analysis and immediately act directly inside the network device. And that's possible now due to advances in programmable network devices. And in particular, there's a kind of device called the protocol-independent switch architecture, or PISA switch. And I just want to tell you a little bit about what they look like. An example of this at Barefoot Networks, which is a startup company that spun out of Stanford, produces products that fit this architecture. There are a number of network interface card vendors like Mellanox and Metronome that do as well. Basically what they do is as a packet goes through the switch, you can parse the packet to pull out information from its header, the IP addresses, the port numbers, things even deeper in the packet. And that parser is now programmable. So you can decide which part of the packet is of interest to you and not be beholden to whatever existing header formats were decided decades ago when the internet was first designed. Some fraction of those bits come along for the ride, and now you can do match action processing with flexible sort of arithmetic logic operations that take place on a subset of packets based on how they're matched in the bits in their packet header. This can be a sort of ternary match on whether a bit is a 1 or a 0 or a wildcard. Some of that information can be stored in a register and used across successive packets to be able to do more sophisticated analysis and control. And some of those bits can flow along to the next stage for further processing. And so there's programmable parsing, programmable instructions that you can use to do arithmetic and logic operations, small amount of state, and a small amount of data that goes from one stage to the next to drive the decisions that get made. So this is a really nice, ripe opportunity for streaming algorithms. We need sublinear data structures because the number of registers is small. We need to work in a streaming fashion because packets are coming every 2 nanoseconds, so we really can't afford to process them twice. But this model is a bit peculiar as well in ways that make us have to design slightly new algorithms to fit it. We have to work in this pipelined fashion. Once we process a packet here and update registers here, we can never go back to those registers again for this packet. For the next packet, sure, but not for this packet, unless we're willing to pay the price of recirculating the packet and taking twice the bandwidth, something we can only do fairly selectively. The amount of memory is quite small. It's just a hash indexed array of registers, so we can't implement even a hash table properly. It's just an array of registers. We can't do multiplication, division, various other exponentiation, lots of things that we might want to do. We can do basic adding, subtracting, bit shifting, sort of bit operators of various types, but because of this 2 nanosecond processing requirement, a lot of operations just aren't in play. And finally, the amount of bits you can carry from one stage to the next is limited as well. So all of these mean that we've got this fairly peculiar, but now fairly general, in that this is appearing in a lot of different networking devices. So we have this new computational model to think of designing new data structures for. So what I want to talk about is some ideas on how to design compact data structures for this space, and I'm going to talk about 3 examples. The first one is looking at microbursts, and this is joint work with collaborators at AT&T, getting back to my roots. What I'm loving about this space is there are a lot of measurement questions I studied at AT&T where I had to rely on inference and sampling and indirect observation and guesswork. And now there's an opportunity to measure these things directly, admittedly with computation and memory resources, but a chance to actually answer these questions in a more fundamental way. So traffic is bursty, particularly in data centers, but even in backbones. And small timescale bursts can lead to a lot of packet loss and delay. And so network administrators are stuck with this tension between wanting to handle these modern bursty workloads, and yet want to buy switches that are cheap, that tend to have fairly shallow packet buffers, and they want to run their networks at very high link utilization to be able to amortize the cost of the equipment they've purchased. These 3 things seem at odds. You want bursty traffic with small buffers driving the links to high utilization. The only way to square this circle is to micromanage the bursty traffic. So what we'd like to do is if a packet queue is built up, a lot of packets, where packets are of different flows or conversations, color here means conversation or flow, we'd like to know when the buildup is high, which traffic is actually responsible, so that we can report it to a collector or drop or mark or selectively push back on the sending of that traffic. So conceptually what we want is when packets come in, we'd like to keep a count of the number of packets of each conversation. And when a packet arrives, we would increment the count, and when it leaves, we would decrement, so that we'd always know the amount of traffic that's sitting in the queue for each of the flows. But we have a problem. We don't have enough memory to store information about the hundreds of thousands of flows that are going through the switch. We can only access each of the pieces of memory in the switch once, so we can't update any data structure twice on entry and exit of packets. And in fact, the entry and exit of packets happens at different locations in the switch, so we just fundamentally don't have the ability to update a data structure twice for the same packet. So what do we do? At a high level, we essentially want to handle departures in batches, so that instead of actually doing deletion of state, we're going to always be adding more and more state as packets arrive, and eventually timing out information that's no longer relevant. So we essentially are dividing the packets in the queue into windows based on the departure time they will later have. And then we can, over a period of time, once this whole batch has left, no longer consider it when we're trying to answer queries. So when a packet arrives, we're essentially adding it to a data structure, and sometime after it departs, it'll expire because its whole window has expired with it. Now, within each of these little windows, we can't afford to store per flow state either. So we can use an existing data structure like a count min sketch to be able to keep track of the set of flows and how many packets or bytes that flow contributes. That actually fits very nicely with the computational model. There's sort of a register array for each of the parts of the count min sketch, and we can pretty naturally manage that. Now, another wrinkle is when a packet arrives, we can't easily ask the data structure, tell me what flow is big. But we can more easily ask, is my flow big? And to be honest, that's actually all we actually care about, because the action we want to take is only on those packets that belong to the heavy flows. So that's sufficient. So basically when a packet arrives, we're going to add it to the data structure, and we're going to also simultaneously ask, am I a bad guy? Is my flow contributing significantly to the backlog in this queue? And if the answer is yes, we'll report the information or act on this packet accordingly. So at a high level then, this pipeline stages in the switch get used to have multiple stages of count min sketches, each representing a window of packet departure times. Packet is added to the appropriate snapshot and sums up the results across multiple count min sketches to get the answer for how many of my packets are sitting in the queue. Eventually, a snapshot is no longer relevant because enough time has elapsed that all the packets of that snapshot have departed the system, and that snapshot can be now reused in a future time interval. So essentially we have a kind of rotating set of snapshots that represent the current state of the queue, plus or minus a few packets, because we've got some amount of error on the sort of boundary cases where some of the packets have a window of left and some have not. So notice here we've got two sources of inaccuracy. We've got kind of rounding errors that happen here, and we've got inaccuracies due to the use of a count min sketch. But the big flows are really big, and so those two errors end up not being terribly significant. If the queue is backed up a lot and the big flows are really big, we'll find them and punish them accordingly. So we implemented this in the Barefoot Tofino switch, and we have it running in AT&T's test lab in Middletown. And the goal is to do a deployment in the next few months in AT&T's operational network to be able to help them detect and diagnose microbursts in packet queues. So that's sort of the first project. Any questions, comments? Yeah.
What's the outlook for richer operations besides addition and subtraction?
So if you're operating in a sort of terabit level switch, probably not very good, to be honest. If you're working in a network interface card, then it's much more reasonable, because you might be operating at 100G or 40G. But right now it looks somewhat fundamental, just very difficult to do that level of arithmetic at that time scale. Yeah. Other thoughts? Cool. So the first example was looking at what flows are heavy in a queue. The second is sort of the dual of that, which flows are heavy on a link. The questions sound the same, but they're a little different. On a link now we're looking at fixed time windows rather than the set of packets currently sitting in a queue. So we'd like to find, let's say, all flows of the k largest flows, or all flows whose total count exceeds a threshold. And the sort of classic algorithm you might think to use here is the space-saving algorithm, which is a pretty natural idea. You keep a table of key value pairs where the key is the flow ID or conversation ID, and the count is the number of packets or bytes that we've seen so far for this flow. Always adding as more come in. Now the idea would be if a new key comes in, if the table is full and that key is not in the table, we need to evict someone from the table to make room for the new key. And the natural thing to do would be to evict the key with the minimum value, because it's the one least likely to be a heavy flow, and replace it with the new flow and allow this flow to be counted. So essentially always evicting the minimum. But the problem is, if we wanted to implement that in practice in a high-speed switch, we can only do one memory access. We can't go through the entire table to find the minimum entry. That's not going to work. So that's a problem. So you could imagine, well, I don't really need to evict the actual minimum. This is a very simple idea. We could just evict the minimum of a small number, like 2 or 3 of the entries, by using 2 or 3 hash functions, and just looking at those entries and saying, okay, well, key 2 and key 4 are the ones I look at. I'm going to evict this one. It's not the actual minimum, but it's pretty darn close, so I should be fine. And that seems like a reasonable idea. But it's still not quite good enough, because we can't access the same data structure twice in the same stage of processing because of the limits of this pipeline architecture we're working with. So go one step further. You think, well, I could do these 2 accesses in 2 stages, divide the table in half and look at one entry in each half of the table. go through and say, well, which one is the minimum? I might go through and say, well, this is the minimum so far. And eventually, by the end, I'll realize this is the true minimum. And now I can decide this is the one I should replace. But this is a problem. I don't know that this one is the true minimum until I've gone here and realized that this one is not, or even the true approximate minimum, if you will. So I've got a problem still. By the end of the pipeline, I know which one I wish I had evicted, but I haven't. I have to actually go back and do the eviction. So still not quite there, but getting close. So the final answer that we came to was to compute the minimum as we go along and to gradually evict the keys as we go from one stage to the next. So for example, imagine here that the first thing I find in the first stage is that this key should be evicted because it's the one I picked using a hash function. This is a horrible decision, right? It's in fact the highest value in the entire data structure. But don't worry, because once I evict it, I'm going to carry it to the next stage and let it compete with whatever I pick as the element to explore in the next stage. And fortunately here, I'll eventually realize I can evict that one and replace it with the key I've just evicted. Okay. So now I'm doing one access per stage and finding the minimum as I go along. And eventually I've replaced, if I need to, the minimum of the D elements I explore with the new key. So this is the kind of thinking process we've been going through in all these projects, is we've taken a classic algorithm from the streaming literature and then relaxed it one step at a time to fit within this computational model. So just to kind of summarize, we're using each of these tables as a simple register array indexed by a hash function. We're using conditional updates to compute the minimum. We're essentially comparing one number against another and replacing the value if necessary. And we're using a small amount of metadata that, notice, does not correspond always to the current packet. Right? We're sometimes passing along metadata from previous packets that was stored temporarily in the previous stage. And that allows us to get relatively high accuracy in finding the heavy hitter flows with state proportional to the number of heavy hitters rather than in proportion to the number of flows. And given the number of flows could easily be hundreds of thousands, and we might only care about the top 10 flows, that's a significant reduction in the amount of space that we need in the switch to do this. So that's sort of the second example. Any questions? Yeah.
So the count is purely additive. There's no moving window.
That's right.
So what about situations where you have, a high burst way at the beginning and then it's completely quiescent?
Right.
And so it looked like a bad actor, but then turned out really not to be.
Yeah. So I think that one answer to that is that you would do this on some fixed window and reset the data structure periodically.
So that's what I was
But there's a second piece to what you're saying that's even more subtle, which is that it might be that something looks small now because it only just arrived.
That's right.
And I might evict things erroneously.
Right.
And so one of my students has a nice follow-up work where you actually probabilistically evict. Instead of actually evicting, you essentially do go all the way to the end of the pipeline. And then you recirculate with a probability that's sort of inversely proportional to the size of the count that's already in the data structure. And that way you're recirculating relatively infrequently, only when you've had a miss, where you found a non-empty, non-matching element in every stage. And then based on the minimum count, you might recirculate that packet and let it replace the true minimum that you discovered.
Could you also use LRU for this? I mean, it seems like that might even work better in some situations.
Yeah.
If you can implement it.
Yeah, I think you'd have to approximate it just because you can only do one access per stage, but that's certainly reasonable. In fact, that optimization ends up being pretty important for accuracy because network flows tend to have a large number of small flows, and once you let a small flow into the data structure, it might kick out someone that's about to become significant.
Yes.
And that's a horrible decision. So we've got a small number of big guys, but we have a huge number of tiny guys. And so this optimization I just mentioned is actually quite important for heightening accuracy over what we have here. Yeah.
So this evicting process seems a bit like the counter bridge overflow, like there was a counter.
Oh, it is sort of similar in spirit. Yeah.
It's sort of the same. You want to propagate to another layer, but it's not. It doesn't. You don't have an explicit thing where these later tables are holding the higher flows, right? That's sort of what happens in that.
Right. Not necessarily. There are other wrinkles here that are more subtle. It's possible in what I've described that a key might be in the table twice. And that's another source of inaccuracy. Like I might come in now and key 4 might come in and evict something here.
Right.
And we don't realize key 4 is already here.
Right.
What we find experimentally is the copies of key 4 meet each other occasionally and add up. So it matters a little bit less than we feared. But there's a lot to do here. We don't have a good analytical model to help us understand all of this. Right now, empirically, it seems to work well, but we don't have a good sort of mathematical model to explain it yet.
And what kind of numbers do you stick to 2 layers? Or?
So in practice, the switches often have like 10 to 16 stages. And what we found is using about 4. Think about sort of birthday paradox kind of things. And basically, we're trying to avoid unnecessary collisions between a pair of heavy flows or a triple of heavy flows. By the time we have 4 stages, we don't see much more benefit. So 4 stages of high height is better than 8 stages of half height, or at least no worse. And so we find roughly 4 stages seems to work pretty well, because we're just trying to avoid large flows happening to collide in the same small set of entries. Yeah, good question. Other thoughts? Good. So the final example I wanted to mention, the first 2 really are focusing on individual switches in isolation. The last one is looking at how to balance load over network paths. And so here, we now, let's say, are in a data center setting where we may have multiple paths that are of the same length between 2 top-of-rack or TOR switches. And we'd ideally like to balance load over those paths based on performance. So essentially what we're going to do is implement a sort of distance vector routing protocol, but directly in the data plane, using link-level performance statistics that get accumulated over the hops in the path. And we're also going to group groups of packets that are part of the same conversation together to force them to go, at least for short periods of time, on the same path to avoid packets getting unnecessarily delivered out of order, which tends to mess up higher-level protocols like TCP. So our goal is for every burst of packets from the same conversation, we want to direct it on what is the current best path to reach the destination top-of-rack switch. That's sort of roughly the problem we're solving. So what can we do? Well, we can send probes from the destination top-of-rack switch that pick up statistics as they hop in the reverse direction towards the source. For example, they might pick up what is the utilization of the link or the backlog in the queue. And that information can be carried on the probe. And as it encounters the next switch, the information can be combined together with a max or an addition operator. So we can essentially, using a very simple operation with order 1 space, continue accumulating a metric for the subpath we've encountered so far as we get closer and closer to the source top-of-rack switch. That works very fine in the switch because we've got access to the metadata that we need and the ability to change the format of the packet to encode this extra little bit of information about the statistics of the path. And then finally, in the other direction, we now need to be able to keep track of which of these next hops is the best way to reach the destination. So just to give you a little bit of a sense of how that works, when a probe comes in, switch 1 might say, oh, if I go, maybe in the past I was going to switch 3 to get to a particular destination with a path utilization of 50%. This probe might come in and say, oh, this path has a utilization of 40%. I can overwrite 40% and the new next hop so that future bursts of packets have a chance to use that better next hop. So this can be implemented with a little register array that is where only one element is accessed every time a probe comes in, corresponding to the destination top-of-rack switch that generated the probe. Now, I also want packets of the same group, little bursts of packets, to go on the same path to avoid out-of-order packets and to help improve the stability of this dynamic routing scheme. So when packets come in, data packets now, we want to be able to group them. If another packet of this flow arrived just moments ago, I don't want to let this second packet pick its next hop independently. I want to force it to inherit the choice the previous packet made. So essentially, I can keep a little table for every flow. I can keep track of the last time I saw a packet for this flow and what next hop was used. So when a packet comes in, I can look at the current time and the past time and see if enough time has elapsed or not for this packet to be entitled to make its own best choice, or whether it's forced to inherit the best choice the previous packet had. And that allows us to make routing have sort of what's called session affinity, where packets that are close together in time will go in the same order over the same path. Again, simple order 1 update. We look at the timestamp, we do a different computation, update the timestamp, and make a decision. So finally, putting all the pieces together, if a data packet comes in, you first figure out what is, for the destination this packet is going to, what's the current best next hop. Then you interrogate the second table and say, am I allowed to use it? Or am I forced to use whatever best hop was used in the past for earlier packets of my flow? And then finally, we can update the next hop and move on. And that's sort of roughly how the algorithm works. So probes going in one direction to update this first table, and data packets going in the other direction to use the current best hop if it's not going to somehow cause packets of that flow to get out of order. And again, here we can implement this completely in the data plane, so we can react in a very small time scale to shifts in load and performance. So the idea here, stepping back, is we'd like to be able to build self-driving networks that integrate measurement, analysis, and control. Instead of measuring using sort of a standard technique like sampling, we'd like to tailor the measurement to the task at hand by doing the analytics directly in the data plane, to do data reduction right as the packets fly by, rather than doing it separately on a monitoring device like a coordinator or central controller. And we'd like to be able to take control action based on those analytics directly. And I think what's nice is now we have network devices that allow us to do that if we're willing to work within this peculiar and yet practically motivated computational model, driven by the need to have switches with reasonable amount of memory that can operate at the line rates of 100 gigabit per second or higher link speeds. And it's just a perfect space for algorithmic foundations of the type that people study here at DIMACS. And so it's been really great. I'm just one example of many people that are exploring problems in this space. And you'll see whole sections on sketches at networking conferences now, which is pretty fun. There's also a lot more to do here. The control actions I mentioned in the talk are quite primitive, right? They're drop something or block something or slow it down. It'd be nice to also add to this much higher level programming abstractions where someone can specify in an integrated way the measurement, analysis, and control that one wants to do, so that one could synthesize the programs that run in the data plane directly rather than implementing those directly. And I should also mention that there is a programming language called P4 that's for programming these protocol-independent packet processors. It's a standard language a group of us have been standardizing in a group called p4.org. And so we've been implementing these and other algorithms in that language. And then those can be compiled to multiple target switches and network interface cards. So this sort of portable language for writing these programs has been an enabler for this kind of work as well, to work across a range of different target devices. So I think in the interest of time, I'll stop there. Are there any questions, comments? Yeah.
Can you talk more about the probe when you determine the best next hop? Is it an active probe or passive probe? And besides using the probe, do we also need the feedback from the receiver to update the table?
So right now we're using active probes. So the destination tour is on some schedule, sending probes in the reverse direction. And we can, let's say, pick up information about queue length or link utilization as we go in the reverse direction. More generally, you could imagine piggybacking that information on data packets that happen incidentally to be flowing in the reverse direction. We're not doing that yet, although I think that's a natural direction to go. And you can even imagine some more goofy things where one packet follows part of a subpath and a different packet follows the rest of the subpath, where you could imagine clever piggybacking techniques that might allow you to avoid using active probes at all. We haven't explored that yet, but I think that'd be a very natural thing to do. Yeah.
In terms of compiling P4 to physical hardware, how different are the capabilities of different models of switches from different manufacturers, or is there subsets of the language that are not going to be able to work with?
Yeah, so there is a notion in P4 of an extern, which is something that's not expected every device would support. A good example might be encryption, where you might imagine some devices support it and some don't. Certainly the multi-terabit per second switches don't support it, whereas others do. A second thing is even if the language is supported on two devices, they might do it differently. So the example I showed of the pipeline is sort of more specific to the ASIC-driven switches, whereas if you had an FPGA, you might choose to make it act like this, but you might have more latitude to have, let's say, shared memory across multiple stages of processing. And that's been actually a challenge for us. It's a reason P4 might not be quite the right language. It's sort of portable in terms of syntax, if you will, but it's not clear that you would optimize the P4 program the same way if you're programming this kind of device than if you're programming an FPGA. And so one other thing we've been grappling with is, is there some other slightly higher level way to specify things that's a little better? And one relates to the question one of you asked about the number of stages. You could imagine wanting to write the program saying, I want something D wide and M high, and pick the right one. In some targets, maybe D should be 4, and others, maybe it needs to be 2. And right now, that P4 kind of forces you specify that explicitly. That's too low level, right? Because it's an optimization decision with a fairly complex utility function to figure out what the right answer is there. So we've been starting to look at program sketches in the other sense of the word sketch that would allow you to keep that degree of freedom flexible before you compile. Yeah.
If I can interject, and Peter, might you be able
Yeah.
to swap your slides and, yeah, we can.
Yeah, please.
So are there any provable guarantees for your proposed strategy, or mostly it's just empirical evaluation?
So for the different projects, so far, no. I mean, I think, and that's a rich area too, I think, to explore. We're sort of approximating data structures that do have provable guarantees, and then not, but our approximations of them, we aren't able to prove things about yet. So it'd be really nice to figure out better ways to reason about that. We haven't figured that out yet. I'll blame Mutu. That's his job.